It's here, like this one, he said it's not working. No, it's in there. My pen drive is there already. Give me my pen drive, it is already loaded there in the PC. Yes, this is my pen drive. If you can turn it on. No, this one. Your main computer. Yeah, this one. Okay.
Yeah, that's forward and previous point.
Good afternoon, everybody. My name is Shubhankar Pati. I'm assistant professor at IIT Bhubaneswar. It's okay. I recently joined, 2 years before I joined IIT Bhubaneswar. I started working on lithium ion batteries about a year before. So Professor Ghosh called me up and said, please give a talk on lithium ion batteries. I said, you give a talk, I don't know anything. So he told, no, just speak whatever you know. I said, okay, I'll try. Probably I was a desperate call. Nobody agreed for this session. So he called me up, I believe. Anyway, don't get disappointed. I'll try to show whatever I have done in last a year or so. Couple of anode materials we started working on. I'll show those and maybe tell a little bit on how to move forward. Basically, my background is I'm an electrical metallurgist. So lithium ion batteries is pretty new to me. So I've sent a couple of students and they did most of the work. So I should acknowledge them. Alright, before moving on, like probably everyone of you have seen this graph again, but everyone likes to see whatever they have seen again. So I'll show it again. As you can see, this per capita energy consumption versus the human development index, the more energy countries spend, generally the human development index is higher. One thing surprised me, how come India is below Pakistan, but I think there is some error in that, or maybe I took it from this UNDP program. But anyway, if you see the light, as far as energy usage in US is concerned, is quite high compared to its human development index. So more or less, Japan or like in these regions, mostly the European, Scandinavian countries lie around here. So they are pretty much, they know how to use energy properly. And we are trying to catch up, we are developing fast. I hope we will catch up very soon. Okay, as most of this energy is non-renewable based, fossil fuel based, and of course we get a lot of CO2 emissions out of it, and this is the CO2 distribution around the world. You can see these African countries where energy usage is very less, this is in I think kilotons today. China, US, most of them are very high side of energy utilization and CO2 emissions. Which I mean, if you think about it, India per capita is pretty low, but as such we are emitting a lot of CO2. So it's a thing of concern for us, and I guess we are already in the path of thinking about that. Okay, so that's CO2. I tried to see recently. I got this figure yesterday only, so got this. I want it was kind of interesting, so I wanted to show this. So I did not at first I did. If you see this line, this is the global mean surface temperature. What it means that Earth has India has around 300 observatories. So they take temperature from each point and they calculate the mean. So similarly, there are many observation points around the world. So they take the each temperature at each place and make a average. So this is this line which has been around. Has been around. For last 1 century or more, it has been like that only. It was below till recently, 1980s, but last 30 years it has been going up dramatically. It's almost 0.6 degrees up towards. And they say, like recently, if you have been following that even climate meeting, they said you have to keep it below 2 degrees centigrade. So that's pretty why they came up with that. If you see this kind of so this is the standard CO2 that has been rising up over the years. If the CO2 remain constant, this will be our global surface warming temperature. It will stay below 1 degree centigrade, which is quite natural. But if we go for a higher rate, if it in faster development, faster growth, this is going to go up. And correspondingly, and now almost 99% of the scientists agree that if it goes up, your global surface temperature is going to rise by more than 2 degrees or 3 degrees and way up if it goes up. Alright? So this is a very bad scenario. We want to keep it at this rate. We don't want to go up, so it's going to create chaos around the world. What it's going to do? I got this some national geographic website. They say if your Earth temperature rises by 1.5 to 2.5 degrees centigrade, this many species will disappear, and this has already disappeared. The golden toad, if you know, so it was found in seacoast of Costa Rica. It has already disappeared. This species doesn't exist anymore. This is a coral reef fish in Australia. So this is the next endangered species. They're telling this is going to disappear. Of course, the polar bear. This is a hammerhead bird. It was found in Massachusetts. It's migrating pretty north towards. So it is also like they're saying the species is endangered and it's going to get there. Similarly, of course, some plant species are also going to disappear if it goes to 2.5. What happens beyond? This is my friend Jake Davis. So he caught a North Atlantic cod. So they say if it goes beyond 2.5, this North Atlantic cod is going to disappear. He sent me this picture. I told him that it's going to disappear soon. Then I wrote him that if it goes beyond that, you will disappear. So he sent me back. He sent me this picture. This is when I was a graduate student doing research in my PhD lab. So he said, you will disappear also. What about me? I said, no, you see me here smiling. At that point, I was not smiling at all. This is like I thought like every PhD student, I think my graduate advisor should disappear. He should become extinct. He is making me work very hard. So we'll see. Who is this lady? Any guess? Oh, she is my wife. She will also disappear. I ask any married man, they will say, at some point or other, don't get me wrong, I love her. But still, at some point I said, I think she should disappear. Okay, if we disappear, you will also the whole world is going to disappear. Definitely. So this is a very big problem. Let's address about it. Think about it for a minute. If you still don't believe that climate change is for real, what about local weather? Is it changing or not? Recently we have been doing drought in Maharashtra and everywhere. Like getting shifted and all these people are doing. So it's happening. So are the temperatures, like city temperatures. I will tell you, like Bhubaneswar, I have been to Bhubaneswar. So I left Bhubaneswar for quite some time, but came back recently. The average daytime summertime temperature has risen by 5 to 6 degrees. That's for sure. And why? All because of this cars. This is where I make a case why Kejriwal is right. So when he says you that you put a hot car one day and electric car one day, is absolutely right. But that's not the solution. You are scientists, you are engineers. We should go for some better methods. Start using renewable energy. Right? In that case, these all energies are intermittent in nature. Anyone who is working in this energy field knows that we cannot store these energies. How will you store solar? How will you store wind? So we need a storage medium. Then there comes your batteries, right? And when at least batteries can intermittently, till we can directly use all the renewable energy, we can use batteries as a storage medium. Now I have made a case for lithium-ion batteries or batteries in general. Recently, you must, all of you, anyone who is following batteries, you see Tesla coming up with a very nice, sophisticated S model. Again, other ionic PHEVs, other physical batteries are coming up. So, but they lack. But still they are only 1% of the total. There are 1 billion cars used around the world. Only 0.1% comprises of all the electric vehicles. If you see that, Tesla has been trying very hard, at least in US they have been trying very hard, put up this power station chargers. You drive in and you park your car, you charge it, then you go home. This is full gas pumps or something, and they have planned to put up all chargers around all the US. Can anyone guess why most of these points are equidistant? I didn't think about it, I saw it. It's kind of interesting. Most of these points more or less equidistant. See, because they have a limited charging. The ferry range is quite limited. You cannot go more than 30, 40 or say 100 kilometers. So you have to recharge every now and then. And this charging time is very high. It's around, if you want to charge it for full, it takes around 4 to 8 hours. If you charge it at least 50% so that you can reach your destination, it still takes around 20 to 30 minutes. So it's still, the batteries are still very primitive in terms of compared to your gas or diesel or petrol. Alright? So we want to increase this. How do we do this? We increase the energy densities of the batteries. So currently it's around 150. Let's say the target is to go to 400 to 500 kilometers, and we need at least 2 to 3 or 4 times more energy density than the current batteries. What to do to this? Your general laptop or something, laptop or your cell phone, you won't need to charge them for a day. You won't need for charge once and you can forget for a week that you need to charge it again. So these high energy density batteries are very, very crucial. That brought me to take up research and think, alright, this is where my problem and focus of the research should be. So I started working on this, like I said, a year before. First I look at this general standard battery device, aluminum current collector, lithium cathode and a carbon copper anode. separated by a separator and electrolyte. So during discharge, it's yes, the lithium what is already charged here. When you are putting the charge, it goes here and you get the current. One lights up.
Current will flow from anode will become the positive when it is being discharged.
Anode.
Copper will become positive at that
Yes,
moment.
electron is like that.
I think it is not correct. When it is during the discharging, discharging carbon will become as a positive, no?
Yes. Oh yes. Yeah. Sorry. I'm sorry. Yes.
When you show this lithium and
Huh?
copper,
Sorry.
what is this composition?
This one?
Lithium versus copper.
This one?
Lithium is ejecting towards aluminum magnetic oxide.
It's like a cobalt oxide.
So that lithium is on copper or what?
Lithium is on copper.
This is copper foil or
No. This is copper foil. This is a current collector.
this is not connected.
Yes, it's not. It's a complete battery, not like your in a half cell. It's a complete battery, not a half cell.
So you are using some anode material after that.
Yes, carbon is
And
graphite.
you are using
Carbon.
what is anode material?
Carbon, graphite. Understood? Yeah, this is not a half cell. Most of this experimentalists always focus on we'll put lithium and it works well. No, it's not. You have to make a full battery. It's a full battery. Understood?
So the carbon will become as a positive anode while being discharged.
Yes, lithium Li plus goes, right? And it takes up electron and sits there. Understood? It's a full battery, not your half cell. Yeah, think about it because it's always we make a mistake of because batteries are different.
So what you call as positive and what you call as negative.
It completely doesn't mean
There
anything.
are, when you are charging it with something, people follow some convention.
Depends on
In charging, the cathode will become as a positive.
Charging whatever is the external terminal,
You-
follow that convention.
Yeah. Think about it. Like it's
Because
just
देखना ना तो वो class 12
oxidation reduction. Thinking like that.
that confusion arises in class 12. Or so देखना ना तो.
Positive and negative doesn't mean anything. Like oxidation reduction. Think about it in that terms. Alright?
When we are in class 12, we are seeing that electrolysis. These are the plus and minus, and during the
Don't think about it. Forget it.
हाँ अभी उसको बाद में करना चलो.
Alright? Okay. So this is a full cell. This is not a lithium foil anyway. I will come to the lithium foil first. Alright. So we want to develop high energy density batteries. Everyone agrees with me, I hope. So how do we do it? First, one way to do it like high voltage cathode. Like we can if this reduction potential versus the Li plus goes up, then the energy density will go up. Or if you can develop high capacity anodes and cathodes. What do I mean by that? If I can store more lithium in the anodes and the cathodes. What is preventing me from finding high voltage cathodes is nothing but my decomposition potential of the electrolyte. So which is around 4.2. This is 4.2 volts. The electrolyte starts decomposing at those potentials and you start getting deposition of lithium. So that prevents me from making high voltage cathodes. So other way to do is, so our aim was to develop, why not develop high density anodes? Okay, but we can say that why not start developing ionic liquids or some certain kind of other electrolytes so that I can boost my, so I can improve my cathode performance. But that's a different kind of research. It takes 2 steps. So the easier way was to do start developing high voltage anodes, high capacity anodes. Okay. So this is when you start your research, you start looking what people have done. So I started looking what are these current anode materials that are used. So I see we are here now. We are at graphite. Right? So we want to be here, lithium, at this line where the voltage against the Li plus is 0, still we are getting high capacity. But this has inherent problems. I'll come to it in a bit. Other one was to look at this alloys, silicon, germanium, tin or antimony or alloys. So while we were doing that, we also thought, okay, why not also see this titanium anodes for high charge. These are high capacity batteries, high energy density batteries, and these are when you can faster discharge and discharge titanium. So I had two students. I put one here and I got put one here. So they started working, and I'll show their work from now on, what they have done. So the first student started working on this synthesis of porous silicon from readily available. Why we decided to do porous silicon? Because we found that people are doing porous silicon, and silicon, everybody agrees that it is around 300% volume expansion. So it's a very bad material as an anode to work with. It breaks and capacity fades within minutes. So, but they have seen that using porous silicon, you can, battery life cycle can be increased. So we thought of devising synthesizing porous silicon. We realized that over time, seeing that all the methods available for synthesizing porous silicon is very, very expensive. All sorts of brutal chemicals, not very clean. So what is the easier way to build make porous silicon? So started looking around why don't we buy some silicon and see. Then I'll come to the minute that how we came up with that problem, solve that problem. And other was the lithium titanate anodes. Other students started working on it for high charge and discharge, faster charge and discharge, low capacity. Okay, first I'll come to the titanates. So these titanates have very low volume change. So that's why you can charge them very faster and very quickly you can charge and discharge. So mostly they are used in buses where you can go and park them, charge it quickly, then use the bus lanes. So these the big buses, they usually just use this kind of titanate anodes. You can withstand large cycles, extend short burst, high rate applications, and the lithium voltage is only 1.55, which is better. You don't get lithium depletion if you do it at a faster rate. You cannot go beyond that. So beyond the depletion. And apparently no solid ACI formation takes place because of course the potential is very low, so the electrolyte is quite stable. Alright, so let's come to the processing. I'm not since we started this program, so it was easier for us to just start from basic and see how we move on. So we started processing, just like typical slurry mixing, then coating, then cutting and everything, and electrode calendering and slitting, and tablet installation. This process we saw, and we tried to make button cells, not the tablet department can forget. And our focus was to study what is the effect of calendering. What is calendering? It's essentially after you coat your electrodes, you take them inside a roll, twin roll, and push it so that you can pack more active material in a smaller volume. So that's why calendering is very important process in actual battery manufacturing process. So we looked into this and what is the effect of this. So first, of course, the formulation study. We tried with PBTL and active material as lithium titanate, carbon black, couple of compositions. This is 65 is around 65 meters per gram. That's the surface area of those carbons, and this is 45 meters per gram. Of course, as expected, we saw the higher surface area of carbon gave a better results. Similarly, percentage of carbon also gave a better result. So 8% from all these later on studies that we did at 8% and C65, which is carbon with a 65 meter square per gram surface area. Now we did a thickness study, like now how if you vary the thickness of the anodes, how it will look. What we did, if you see, these are C rates are nothing but how fast you can charge and discharge your batteries. As you can see, luckily we got a commercial. There is a company called Altern, and they gave us commercial lithium titanate anode to check how good are their process. So we checked it exact same. They coated the electrode and gave it to us. We just made the button cells out of it and tested. You can more or less see up to 2C. All of the batteries are, all of the button cells are performing quite well. But beyond at a very high C, 5C, you see that 250 only sustains, others fail. Okay, so which is kind of expected because we thought literature is available, standard literature. So when you are charging at a very fast slow charge rate, charging and discharging, the whole lithium titanate material is available. But when you go at a very fast rate, slowly, the availability or the diffusion time rather goes down. So that's why you see that thinner the electrode, better it is. But actually you cannot do that in practice. Practice you have to make a electrode sufficient thick enough so that you can pack more and more anode materials. That's your goal. So now once we have formulated the calendering part and the thickness and the formulation, we went for calendering, which is essentially nothing but reduction of thickness to make the to pack more active material. So this is a comparison of a ATO with graphite. You can see more or less at 20% correct thickness, the density and the density are more or less same. So this slide doesn't mean anything much, but I just wanted to show you. So more or less we are in a similar trend of calendering, just to show this. It's basically this electrode density, how much active material is packed in the electrode and the whatever thickness reduction you are going for. Right? So it's more or less the same for ATO and graphite. After calendering, we did again the take test. We see this is theoretical. Of course, at 1C it's more or less same, but once you go up, you can start seeing the effect of calendering. This data is still not very clear why this is happening. We believe there is some because this while we are calendering the electrodes, what we are doing is essentially changing the triple phase boundaries. What we call is as like the electrode, the active material, and the electronic conductor triple point junction. So I am a solid oxide physician guy, so it's easier for me to understand that way. So if they call the triple phase boundaries, where your electrolyte, your lithium titanate, where the lithium goes sits, and the carbon contact, where the electron goes. So they kind of change the shape, the area, the length, and everything changes. So that's why this is happening, but still I am not sure why it is doing it. Then we did the comparison with the commercial anodes as well. More or less similar trend. At 2C, sorry, at 2C it's almost the same, but again when you go for 5C, it starts, your commercial even degrades, but now the 42% calendar still remains the same. It's still performing better than the others. Interesting to note that when you again decrease the charging rate, everything goes back to its original performance goes up. Then finally we did a life cycle test. This was kind of anomaly compared to graphite. What I mean by that is that this uncalendared showed a better life stage compared to the calendared ones, both for commercial and for our material. So I do not know if anybody knows why it is happening. Would be happy to let me know. But because we started looking at literature, in graphite exactly the opposite happens. The calendared ones has a better life compared to the uncalendared ones. Alright. So yeah, still this data I don't know how to explain it. I recently got this data, so not able to comprehend why it is. More or less this is
just one cell measurement, right?
no, it's many cells actually.
So do you have a error bar?
Error bar is there, but it is not plotted. I think we can measure 4 or 5. So probably that would be a good.
And it's 4 or 5 cells of the same coatings, same everything?
Yeah.
Because I always believe that when you have sugar measurements of this, it should be a,
Most of these data are from 3 to 4 cells.
but from the same, electrons should be punched with the same coating and, same
Yeah,
types
it's
of electrolyte.
is huge.
Because all this is very difficult to figure out which parameter is playing a role. Because calendaring, that should not happen.
Now it should go up. Like maybe I'll make it do one more.
In what, which electrolyte do you use?
I like this.
EC?
ECDM.
DMC cell. You find any kind of SCI on the first
No,
charge?
no,
Nothing.
no, nothing. That's yeah. This data is still new, so I'm still trying to comprehend what is happening. Okay.
What was your this half cell?
This is half cell. Oh, I'm sorry. All these experiments are from half cells. Yes. Alright. So this is what overall what I is comprehend. Like calendar give a better rate and cycle rate for graphite, but not so for us. So I'm not sure why this is happening. Probably like that this maybe the temperature phase area is changing, is doing something somewhere. So I do not know yet, but I have a feeling that we can understand this through EIS. Probably, I'm not sure. This is a hunch by hunch I have. If anybody knows about EIS, this is essentially you give a AC current and measure the impedance at different frequencies. So you plot your real part and imaginary part, and you see how at what frequencies each reaction takes place. So again, this is extensively used in your solid oxide fuel cells and other solid electronics devices. So I thought of going to this route to figure out how my calendaring is affecting my performance. So more or less you can see that if this is your separator, this is your insulating layer, which is absent in case of NTO. Then you have a charge transfer reaction taking place, LIB going to LIB. Then diffusion through the electrolyte, this diffusion through your active material, and finally, if any change in crystalline structure or something is happening, will be captured in this kind of. Plotted a couple of impedance spectra, but still in the first place I am not able to show those data yet. Then this data I will show from the theoretical study of a colleague of mine. So I work with him, Dr. Anode. So he does DFT calculations using VASP. So more or less you can see the intercalation voltage around 1.55 or 1.6 around this. So this what happens is like your spinner structure changes to a rock solid structure. This is an Ni7, this is an F4. So he took this data, this structure, calculated the structure parameters and everything. I am not an expert in it, so I don't know. If you ask me too much, I will raise my hands up. So this spinner structure changes to a cubic structure. Using this structure, the lithium goes from the tetrahedral sites, 8 sites to 16 sites. 16 sites and sits there. Using this structure, we calculated the it came out 1.6. 1.6 theoretical voltage came out around 1.6. This is a process of changing between playing around with this first attempt. It does some band calculations as well. And see LI4 is insulating in nature, but LI7 has some is electronic little bit in nature. So the conductivity, electronic conductivity improves once you start putting in this chemical. So idea was to develop this, then go for standard doping. If you can pick up some standard molecule or some material and do a, people have done it I think. But anyway, it was an exercise for us to learn as well, to see what doping does to the electronic structure. So you can do this kind of calculations and it does it easily, he says.
Negative voltage here, negative voltage can be E minus here will be minus 5 or minus 7.5.
E minus here.
Then it will happen in the cell planet or
E minus
data, or it will happen actually in the
this is actually I am not expert in DFT calculation. What I understood from it is that there is a band gap here. There is insulated in nature, but this is not. So if you really want to, I can give you email to. I am not a actually experiment with this. I just use this help just to show probably anyone who is in expert in DFT can.
No, it has developed a metallic character.
It has developed a metallic character. That's what.
Actually, the thing is that zero is actually the Fermi.
Yeah.
And Fermi energy, if you have some density, then that means there will be some conduction.
Yeah, this is metallic in nature. This is starts conducting electrons. This does not, because it does not have a.
these are the EMF now.
No, these are electron volt, not volt. It's not cell voltage.
Electron. Energy.
It's energy.
Energy.
So the negative energy means it will be absorbing energy at that time.
Yeah,
So
you
the
are
last
asking.
electron, what it means is the point where it is zero. That
Yeah,
is the highest. That is the highest energy. Electron is there. Okay. So in this one, the highest energy electron, that band is finishing there. Okay. Here it is in the middle of the band. So you have a half filled band actually, so it can conduct.
Yeah. So yeah, again, this is not my data. Just he helped me out to find out. So if you really want to know, I can put it.
And for negative energy.
Negative, that is a scale actually. It is E minus EF. So you are taking the EF at zero.
So if you really want to know, I can put in contact.
मैंने जो हमने चला ना हमारी
Because I don't know. This is not my area. Okay. So the other part I was talking about. Let's move on to that part. So
what is the pore size?
pore size.
Pore size of the silicon. What size of the pore?
It's a nano range. It lives in nano range.
How you have synthesized?
Etching.
Huh?
It's wonderful. Like we will show
You have just put something there and you have etched it out.
Etch it out. It's beauty. Like
Now, why I am telling you? Why I am telling you? We have recently published a paper,
Oh, we did.
which is actually explaining something. It's a very different mechanism that why the expansion reduces. Okay.
Porous silicon.
Not porous silicon. It is obviously it's going to be porous silicon. Yeah. See, the first work in this kind of thing was actually reported by 2011. Stanford.
Yes.
Harvard or something. Yeah.
So
Yao was the first
they
one.
were working on hollow tubes.
Yeah, they were actually Basically, they deposited silicon on those and then
but
they etched out actually. But they deposit in chemical vapor deposition.
it's very expensive.
Yeah, that's what I'm saying. That I'm asking how we did it. Actually, what we can do is your experimental data and our theoretical simulation, we can combine them. We can just publish in journal RLS. Because we can have another. So what is happening is that what we have shown through molecular dynamics that there is a lowering of density. Okay, and this phenomenon is known. It's called nanoclass. It's for process lighter data. And what we showed is actually by when the lithium result collects in this kind of system, the expansion is practically reduced.
Yeah, it's up to like if you have 70% of this
So we have actually, so we have given the reference with.
So yeah, I mean, this slide everyone knows, so it's up to significantly high capacity compared to the current graphite or carbon. So it's basically because of the other formation. So I am can move on.
So nano, what is the nanometer size of the pore?
I think it's 30 nanometers.
30 nanometers. Then what is the fraction?
You can see, yeah, it's around 30 nanometers surface pores.
What is the fraction of the pores?
Fraction.
Porosity.
Porosity, surface area we measured, it was around twice as published research data. So you can come here, around 75%.
Porosity.
75 meters per kilogram. Surface area. Surface area.
No, I am saying the fraction of the pore.
How do you measure that in porosity?
No, I'm not asking how. What is, have you estimated the fraction of the pore?
Fraction of individual particle. Individual particle.
No, the pore, it's a porous structure, right?
Right.
What is the fraction of the volume fraction of the pore?
That can be calculated by from the surface area.
Yeah, but I'm not calculating.
So you have not calculated that.
But yeah, it's but again, it's all a calculated part.
Yeah.
Shall I move on?
Yeah.
Anyway, so as everyone knows, like this. So his huge volume expansion takes place. So like silicon breaks down very easily. And another issue is the shale formation, which everyone probably knows already. So to address this, volume expansion and the shale formation, we thought of synthesizing porous silicon and then coat it with some carbon or some other material to prevent the shale formation. So the first part I will explain now how we synthesize the porous silicon. We looked around how do they do it. Everything is pretty complicated. They do electrochemical etching, metallosmic reduction, chemical etching, lot of very cumbersome, long process. Then we thought, okay, what's the better way to do it? We had some knowledge from earlier about aluminum silicon alloys. How can we etch out aluminum? We knew very well that aluminum reacts vigorously with potassium hydroxide. What we did was I took this alloy. It's a bulk, readily available alloy. You can go into the market and get it. It's pretty cheap.
So what you did is actually you build actually with aluminum.
It's pretty standard.
Standard alloy.
Standard alloy. Every metallurgy lab has this.
Have you published it? You should not show so much details.
We have filed a patent. So.
As a teacher, you are telling you should not show so much.
This is a workshop. We have already filed a patent on this.
That is it.
So they recently filed a patent on this. Yeah, and all about the student did, so I'm just showing you. And we have optimized this in the range at which it gives the maximum porosity as well. So it's like the idea was to develop a low cost material and low cost process. So at some point probably you have to recycle it away because this at times can be very expensive. What it does is, so while we are doing this work, we started to see this data was available, but this guy started publishing this data. Then I thought, okay, just done. Research, like why I'm doing it, it's already there. While we're thinking about it and started doing, they already published it. But then we realized they were targeting only this. They specifically said that you have to target this part, the very high aluminum content and silicon, which was exactly opposite of us. We were happy that we were already targeting only high percentage of silicon, so that we can remove only little bit of aluminum. What it does is, if you see the process, they were using NOH as reactant. It forms silicon, and none of the aluminum gets only etched out. The silicon stays as such, and you get fine silicon crystals. But in case of this method, this whole silicon is a matrix, aluminum is the your precipitates inside. So what it does is it reacts with silicon to form some silicon hydroxide, which is not present in this case. So we get some silicon hydroxide that etches out some of your silicon as well. So that's why you start getting a porous structure, and we call it like aluminum etching plus anisotropic etching of silicon. This is a pretty standard. So I'll come to that technique in a bit. So then again we did that extra standard stuff. So of course we started with aluminum silicon and we ended up with high purity silicon. And this was the core structure which I already showed. If you see that the porosity is around 10 nanometers or around 10 maybe 100 nanometers. Did a surface PET characterization and use VGH online type analysis. Yeah, the surface area was around 80 to 90 meters square per gram and meters. Then again this core diameter was around, like you asked, core diameter is around 20 to 40, and some diameters like the bigger cores are around 60 to 80, mostly around this range. So what we believe, the theory behind this silicon etching, we took some pure silicon to understand why it is doing so, and did some pure etch and saw that you try any other leachant, like say NOH or say HCl or anything, acid etching, it doesn't do anything to the particles surface. But if you use potassium hydroxide in certain composition range, you start etching out some of the silicon. Why does it? Because we believe that if some purpose temperature is there, the surface has some dangling bonds based on the what surface is exposed to the air, what is in the surface. Sometimes it is like 2 bonds, sometimes it is 1 bond, and maybe it's 3 bonds at times when it's a different plane at 1, 1, 0. So it attacks, this OH attaches to this Si on the surface and gets out, forms SiOH and comes out in the solution. So this data, you can see that compared to all the existing methods, we are almost twice the size, twice the area, which is quite good. But we tried just using this material in a battery, but it did not work out well. Battery died like within a couple of cycles. We have to coat it with something, or else it's impossible to. We did try. It's not that we did not try to make a battery, but no point showing that. Alright. So how do I see the future here? I think next we move to titanium, lithium titanate. It will increase conductivity and maybe extensively use electrical impedance spectroscopy to understand the processing methods and the parameters, which I think we can do it if we have pretty good hold on how to do it. And maybe finally coating in terms of in the silicon anode, we want to coat it with something, so that's the maybe carbon or some other lithium based elements. show this slide again because this is kind of important. This is where I started lithium-ion battery research work. Although we are here, my aim is at some point all of us should go to lithium anodes and prevent the dendritic growths if some way we can. We were discussing the other day about how to do that. We can set up some fundamental experiments to understand how to move towards lithium anode. Okay. So and also some maybe people since the workshop one suggestion is to try ionic liquids so that you can use go for better cathodes as well. Okay. Thank you. Yeah, if you did not understand anything, please then suppose.
Send me some of the papers, so silicon, how